Welcome back to this unit on non-spherical particles. The next part will deal with the orientation representation of non-spherical particles. In order to represent a certain position, rotational position of a particle, we have different options. The first, more traditional way is to use the so-called Euler angles. They are typically denoted as alpha, beta and phi. These three angles, introduced by Leonhard Euler himself, describe the orientation of a rigid body with respect to a fixed coordinate system. So essentially, this is a sequential application of rotation angles to this coordinate system. In contrast to this, one can define quaternions. These have been introduced by Evans and Murat in the field of molecular dynamics and have been extremely successful also in the field of DEM. Here a set of 4 numbers, so Qi is a vector consisting of 4 entries, that obey a special rule for multiplication, can effectively be used to describe the orientation of a particle in space. We will focus also on these quaternions, and there are multiple reasons. First, they are numerically more stable and efficient. The reason for that is that, as you will see later, we just have to perform simple multiplications. If we would have made the decision to use Euler angles, we would have to tackle singularities when applying these angles, and in addition, we would have to perform expensive, computationally expensive sinus and cosinus functional evaluations. The second point is that the quaternions can be renormalized, you will see this in a second, to avoid accumulation of errors. This ensures energy conservation in our simulation. The rotation matrix A that we have seen before is also directly related to quaternions and can be readily calculated with simple multiplications. And last but not least, wherever you look into the field of non-spherical particles, you see the usage of quaternions. So they have been really very, very successful. So what is this magic quaternion? A quaternion can be thought of as an extension of a complex number in 2D. You might be familiar with the representation of rotations in 2 dimensions with complex numbers. For example, here, if we have the real axis and an imaginary axis, we can describe a certain orientation in this plane here by this angle phi here. So we use this imaginary number I to represent this second coordinate axis. For this 2D example, you will see that this formalism gives an extremely elegant way to represent a generic rotation. For example, to apply a rotation with an angle phi to a vector that's oriented along v, it is enough to simply multiply it with this rotation operation here to arrive at this rotated vector v prime. So you see it's simply added here to this angle theta. So for quaternions, we can think of an extension of this concept to 4 dimensions. Specifically, quaternions are a 4-dimensional division algebra represented by a 4-dimensional vector with the entries q0, q1, q2 and q3. And the numbers here I, j and k are defined that we guarantee this relationship. This is not important for us if we want to apply it to the DEM. What is more important is that the quaternion has the following nice property. So if we sum up the squares of all these components here, we must arrive at 1. So this is useful if we want to renormalize the components of the quaternion, and the reason for a non-conservation of this property could be, for example, numerical errors. I've also promised you to show you the connection between the quaternion and the rotation matrix A. Here you see it. It's a comparably simple connection by just multiplications and these square functions here. Also, the last point is very important. The time derivative of each component of the quaternion can be connected to the current state of the quaternion and the angular velocity in this particle fixed coordinate system. These angular velocities, as you will see later, can be obtained by integrating the angular momentum equation in the particle fixed coordinate system. Let us finish our discussion of quaternions with a funny side note. It's important to know that the product of quaternions, so a serial application of quaternions, is non-commutative. It means if we apply it in a different sequence, we get different results. This can be visualized by rotation of this dinosaur here. If we have two rotations about this axis and this axis, you will see that we start from the front view to the side view, and if we then twist it again over this axis here, we go to the top view. However, if we do this rotation first here, then we get a different result, as you can see. So this is important, and more information about quaternions, group of matrices, etc., etc., can be found in this very nice textbook of TAP. Let us now continue to the shape representation. We have already outlined three dominating approaches. The first one is the so-called multisphere approach. This approach is also known as the glued sphere, the composite sphere, or the sphere clump approach, and is visualized here in this image. As you can see, we simply rigidly connect multiple spheres to a larger non-spherical particle. This is also the basic idea behind this. It's very simple. The challenge is that the properties of this composite non-spherical particle must be evaluated with care. For example, the moment of inertia tensor or the center of mass of such a particle must be calculated not simply by summing over the spheres, because they overlap. This would give an incorrect result. In contrast, we will see later that, for example, Monte Carlo integration can be used to evaluate the properties of such a multisphere non-spherical particle. Let us now consider the advantages. It's a relatively simple extension of a sphere-based DEM simulation, so the contact detection, for example, can be taken as it is from sphere-based DEM. Any shape is in principle possible. Of course, we need more and more of these small grains here. It's widely available in the code because of this relatively simple extension to the sphere-based DEM. As always, there are also drawbacks. And the first is that it's impossible to have sharp edges with such a glued sphere approach. Also, there is always a slight non-convexity, so artificial roughness. Non-convex means that if we connect 2 points on the surface of this particle, the line connecting these 2 points will leave the particle. Also, if we have realistic shapes, so many subparticles, we will need a lot of memory, as you will see. Last, there is a need to modify the contact law in case multiple component spheres can be in contact with another particle. This has been discussed in CODAM. It's a detail, but it's often overlooked. Let us now move on to the spherocylinder approach. Here the particles are also known as capsules. They look like this. So we have a cylindrical part and 2 half-spherical caps. Spherocylinders are a special case of spherosimplices, and these spherosimplices are defined based on the idea of a motion of a sphere that is dragged along a skeleton. And this skeleton in general can have any shape. If the skeleton is now a straight line, for example here this dashed dotted line, we get a spherocylinder. The advantages of spherocylinders are that first, it's a relatively small extension to a sphere-based contact detection algorithm. It's not trivial, but it's absolutely doable. Compared to spheroidal approximations, spherocylinders offer a fast contact detection. And last but not least, they are obviously very well suited for elongated bodies such as fibers. Of course, these fibers must be rigid. There are also drawbacks. Again, there is no possibility of sharp edges. It's impossible to get it with this approach. Also, as it is clear, we have only a relatively simple shape and we have almost no geometric flexibility. The particles must be always convex. Let us now move on to the last shape representation, and these are superquadrics. The idea here is to describe a three-dimensional surface with an equation that has 5 parameters. I don't show you the equation here, but believe me, there are 3 length parameters, a, b and c. You see, if this a, b and c is equal, we arrive at the sphere. And there are 2 blockiness parameters, n1 and n2. Depending on this blockiness parameter, especially if it goes larger than 2, we can model almost flat surfaces. So the advantage of superquadrics is that they have a big shape flexibility with the 5 parameters at a reasonable computational cost. They are relatively widely available, and the volume and moment of inertia tensor can be analytically calculated. This is nice. The drawbacks are that there is an iterative algorithm for contact detection and that typically we only allow for convex particle shapes. That doesn't mean that superquadrics cannot be used for non-convex particles, but this specific algorithm, for example, can only handle convex particles. Here is some eye candy to round off this part of superquadrics. You see, these are like M shaped particles, these are like cuboidal particles, and these are really MODEMs. Finally, here's the eye candy from the PhD thesis of Tivadar Pongo from the University of Navarra, showing that nowadays you can really track thousands of superquadrics efficiently. The final slide discusses the computational expense. For the sphere, we need the lowest amount of memory and the smallest computation time. And this increases steadily up to this multisphere approach that has the highest memory demand. Note that these capsules are spherocylinders. The cuboidal and dodecahedron shaped particles we have not discussed. These are polyhedral particles, but you see that they can have sharp edges, and this is an advantage, at a reasonable memory demand. However, the computation time of these non-spherical particle shape approximations is typically excessive. This is it with this part on the shape representation. I hope you enjoyed it. See you next time.